Thank you. So I want to talk about a Tameness criterion for modular R-bar, where R-bar is a Mod P Galois representation. So everything I'm saying is joint work with Levin and Morra, unless otherwise stated. So I want to start by fixing a prime P. So this will be fixed throughout the talk. And I want to start with an example, which illustrates the phenomenon I want to discuss further. So let's take some integer, some natural number n, and which is co-prime to p, and I want to look at the cohomology of the modular curve at level n with some coefficients, mod p coefficients. And this has an action of the Hecke algebra. So, so M here is going to be some maximal ideal of the Hecke algebra. And I want to assume that this corresponds to some eigenspace here. So in such a situation, to M I can attach a Galois representation, which I'll call R bar. So it's a two-dimensional mod P Galois representation. Okay. So this implies that this Galois representation. So the fact that this cohomology group is non-zero implies that this Galois representation has a characteristic zero lift, which is crystalline at P, and moreover has Hodge-Tate weights A plus 1 and B. So let me write that down. So so in particular, the local Galois representation has a crystalline lift of weight A plus 1B. Okay. So this follows from a crystalline comparison theorem. So the fact that it's crystalline reflects the fact that P does not divide n. And in fact, this is an equivalence. So if some global Galois representation has a crystalline lift and it's odd and irreducible, then you'll be able to find this Hecke eigensystem in this cohomology space. Okay. So this is maybe a little surprising, this fact at first glance, because this is a global property and this is a local property. So the seemingly global property is, in fact, it turns out that it's purely local. Okay, so so let me give an example then. So this kind of tells you, say you have a Hecke eigensystem and you wanted to see in which local system you should look for that eigensystem. This tells you where to look. So you just think about where the local representation has a crystalline, in what weight the local representation has a crystalline lift. So in this example, let's take P to be 23, and M will correspond to the Ramanujan delta function. So in this case, I meant to give this a name, so let me give this a name. So let me call this FAB for short. Okay, so I want to see when this cohomology group localized at M is non-zero, and this happens if and only if sigma is one of two things. It's either sim 10 of fp squared or a twist of it by determined to the 11. So these two local systems. So this is if the sigma is an irreducible GL2 CP module over FP squared. Over FP bar. And I'll call such a thing a Serre weight. Okay. So, okay. So why is this fact true? The reason is, if I look at this equivalence here says I should look at crystalline lifts of R bar restricted to the decomposition group at P, and if I restrict to the inertial group subgroup at P, then this is going to have the following form. So it's going to be a direct sum of two characters. So here, one denotes the trivial character, and omega is the mod P cyclotomic character. Okay. And I want to point out that this is the same as omega to the trivial character is the same as omega to the 22nd. And so we can see that R bar has R bar restricted to the decomposition group has a crystalline lift of weight 11 and 0, just by taking the cyclotomic character to the 11th and the trivial character. And it also has a crystalline lift of weight 22 and 11, corresponding to, instead of taking the trivial character here, one takes the cyclotomic character to the 22nd power. And the key thing to note is that, so what typically happens is one doesn't get a direct sum, but one gets a non-trivial extension, in which case only this direction would give you a crystalline lift. So there wouldn't be a crystalline lift in weight 22 and 11 if this were non-split. So this is kind of a special case. So typically one just sees. So typically one can only find a single Serre weight, which will make this non-zero. Okay. And what's special is the fact that this extension splits. So the slogan that I want to enunciate is that tame representations so this is a tame representation, and being tame is the same as the restriction to inertia being a direct sum of characters, or just the restriction to the decomposition group at P being semi-simple. So those are all equivalent. So the slogan is that tame representations like this one have more lifts. In this particular case, more crystalline lifts of different weights. Or also they have more modular Serre weights. So that's what I'm calling this sigma here. So the main goal for today is to make this slogan more precise and discuss some higher rank cases and the geometry that underlies this phenomenon. Okay, so so as I stated, this is a priori a global question, but it turns out that it has a local nature. So when one discusses generalizations of this, one doesn't expect that the global context plays such a big role, but it's good to just have one fixed. So let me do that. Sorry about this. Okay, so I'm going to go over this a little quickly because I think everyone's seen similar definitions. So I'm going to start with a totally real field. And for technical reasons, I'm going to assume that it's not equal to Q. So this is just so that certain trace formula arguments can be used. Okay, so I'm going to consider some CM field over F plus. And I'm going to make the assumption that P is unramified in F plus. Okay. Maybe at the very end, I'll say something about how to relax this. And I'm going to further make the assumption that all places in F plus, which are above P, split in F. And we'll see why that's important in a second. So I'm going to consider an outer form of GLN, which is split over F, and definite at all the infinite places. So the assumption about the splitting behavior of places above P guarantees that locally at P, or locally at places above P, this will just look like GLN. Okay, and I'm going to just take I'm going to take the restriction of scalars with this, just to make my life a little bit easier. Okay. So let's consider a compact open subgroup of the Adels, the finite Adels. So let me put that in. And I'm going to assume that the part away from P is sufficiently small, and the part at P is going to be a hyperspecial compact open subgroup. So I can choose some nice integral model at P, and I'm just going to take the ZP points of G. Okay, so I wanted to find automorphic forms for this group. So that would just be this space. So I start with some UP module W, which will be the coefficients. So this will be like this will play the role of the sim A minus B tensor determinant to the B. And I'm going to look at functions from this Adelic quotient to W, which transform in this way. Okay. And then, as usual, this space has an action of the Hecke algebra, and I'm going to take some maximal ideal at which this space is supported. And to such a maximal ideal, I can attach a Galois representation. So this is a certain. So this is an L homomorphism, but there's a pretty down-to-earth way of thinking about this. It's basically just a Galois representation. You can think of it as a Galois representation from the absolute Galois group of F. Okay, and so as before, I want to study the Serre weights for which I can find this Hecke eigensystem. So I'm going to let that be the weight set W of R bar. Okay, and this will play a key role in what follows. So that's exactly the analog of this this set of two elements over here. Okay. So these are again Serre weights up to isomorphism. Okay, and then just for notational convenience, I'll call the local Galois representation at P rho bar. Okay, so that was probably fast. So let me see if there are any questions.
Dan, I have one quick question.
Sure.
So in the definition of this set of Serre weights, is the prime to P part sort of allowed to vary, or is it fixed, or does it matter? Or like this UP infinity?
Yeah, that's a good question. So let me say that it's allowed to vary.
Okay, thanks.
Yeah. Thank you. Okay, so piece of paper slightly too big. Actually, I should switch it this way. Okay, so let me now write down the Tameness criterion. So here's the theorem. So I'll call this Tameness criterion version 1. And if there's time, I'll discuss a second version. Okay, so assume that the local Galois representation at P is very generic. So without writing this down, let me just quickly say what I mean by this. So if you recall in this first example, I had these exponents, 11 and 0, and those are called inertial weights. And the assumption that rho bar is very generic means that the inertial weights are going to, so there's going to be some implicit polynomial, which doesn't depend on P. And I want that when I evaluate this polynomial at the inertial weights, which are integers, then it's not divisible by P. Okay. So since the polynomial is independent of P, as P gets large, then most things will be very generic. Okay. So remember, there's some implicit polynomial which exists but is not explicit, and so I can't write it down. And in the second version, if I get to it, then it can be. Then in fact, you can weaken this hypothesis and make the polynomial explicit. Okay, so there are so the following things are equivalent. So rho bar is tamely ramified. Okay. So the next thing is that this weight set is equal to a certain set predicted by Florian-Herzig. So this is some explicit set defined by Herzig. It's defined combinatorially, and it'll come back in a moment. So I will I'll bring it up. Yeah, we'll see it again. Okay. but for the moment, don't worry about it. And then so there's a last condition, which is just about the size of this weight set. And it's that this weight set has the same size as the number of Jordan-Holder factors of a Deligne-Lustig representation. So let's say R is a generic Deligne-Lustig representation of G of FP. So if R is generic, then the number of Jordan-Holder factors, so the number of Jordan-Holder factors is uniform across all generic Deligne-Lustig representations. So that's just some number which has some combinatorial interpretation. Okay. And in fact, it's always true that this will be less than or equal to this set, or there will always be an inequality. So this makes the slogan precise. Okay, so are there any questions about the theorem? So although I didn't say what this W question mark set is, hopefully it was clear that the SS means the semi-simplification of rho bar. So while I didn't say what the set is, let me just remark that 2 immediately implies 3 just by its definition. Okay. So in fact, it's defined by some process that involves taking the Jordan-Holder factors of a generic Deligne-Lustig representation. So 2 implies 3 is immediate once one knows the definition. Okay, so I'll devote most of the talk to explaining some of the other implications in this theorem. Okay. I did before. So the proof of this theorem uses the geometry of moduli of Galois representations. So let me quickly summarize some results of Emerton and Gee on this topic. So first, they construct a moduli of rank n phi gamma modules, and they prove that it's a Noetherian formal algebraic stack. And next, they enumerate the irreducible components of the underlying reduced stack. And they enumerate in terms of CR weights. Yeah, maybe I should remark that. So in our situation, G of FP is going to be a product of GLN of FQs, where the Q are going to be the residue fields of places lying above P in F plus. And it's not too hard to reduce to just one factor. So let me just assume that P is inert in F plus. So in this case, the Galois representations, which I'm going to parameterize, are ones of G F plus sub P. Okay. So I'm taking the completion of F plus at P, and that's going to be my p-adic field. Okay. So yeah, so lurking in here, there's some p-adic field which is not mentioned, and that's exactly the completion of F plus at P. Okay, and these Serre weights are just the Serre weights of the G of FP then. Next, they construct a substack of Xn, and this parameterizes potentially crystalline representations of some fixed type, lambda tau. So lambda gives the Hodge-Tate weights, and tau gives the descent data for the potentially part. And this is a p-adic formal algebraic stack. It's equidimensional. And in fact, it has the same, so its underlying reduced is going to have the same dimension as the dimension of Xn red. And it's just a union of the irreducible components. So the irreducible components of this stack are parameterized by some set of Serre weights. Okay. Okay. So are there any questions? Again, that was a little fast. If you recall from the first page, we want to think about lifts of mod P local Galois representations. Okay, so say for instance you wanted to know if a rho bar had a lift of type, a potentially crystalline lift of type lambda tau. So to know such a thing, one way to investigate this is to figure out which irreducible components rho bar lies on. So rho bar gives an FP bar point of Xn, or Xn red. And first you'd like to know which irreducible components it lies on. Then you'd like to know what are the irreducible components corresponding to X lambda tau. And if rho bar lies on one of those irreducible components, that means that rho bar will have a lift of type lambda tau. Okay, so to answer this lifting question, again, it's reduced to two questions. So what are the irreducible components any given rho bar lies on? And what are the irreducible components of X lambda tau red? Now, unfortunately, the definition of these objects doesn't tell you very much information about either of these questions. So, next, I'm going to discuss some results on these questions in some special cases. So maybe I should pause again because that was probably fast. Okay, so so to do this, I have to explain quite a lot, and this will just be a black box for the rest of the talk. So I want to define what is a certain end variety. So I want to consider, so here, this is the dual group of G. So I want to look at the loop group of this. And I'm going to quotient by an Iwahori subgroup. So this is a lower triangular. lower triangular Uehori subgroup. And I'm going to put a certain closed condition on this, which is that I do, so t is my loop variable. So I'm going to take some representative of a coset, and I'm going to do t squared a inverse dA dt, and the condition is that this lies in the Lie algebra of the Uehori. Okay. And yeah, so it's a bit of a mouthful. And so this defines some pre-sheaf, and I want to sheafify it. And it turns out that this sheaf is representable by a nice invariety. So if I just took this quotient without this condition, this would give what's called the affine flag variety. Okay. So any questions so far? So hopefully it's clear that this condition doesn't depend on the choice of representative. So you would just conjugate by, it's probably not, yeah, I mean, it's easy to check that if you right multiply by something here, that corresponds to conjugation on this element. Okay. Well, maybe not conjugation, but at the very least, you'll stay inside here. Okay. So in here, there's a certain I want to take a certain union of irreducible components. Okay. And I want to take the underlying reduced scheme structure. Okay. And unfortunately, I can't be too explicit about what this is. But note that both of these things, they have an action of the following. So in fact, this condition, if I left multiply by a constant matrix, then it's easy to check that this condition is invariant under that. So you have an action by just G hat, but I want to consider just the diagonal torus inside of there. And there's also an action of GM by scaling T. So this is called the turning torus action. Let me just call this T tilde. Okay. So one can check that this condition is also preserved under the scaling action. And let me just, so it's hard to process what this definition is, but let me just give an example. So if G hat is GL2, which corresponds to the case where G is GL2, then this M gen red is just going to be infinitely many copies of some finite chain of P1s. The length of the chain is roughly P. Okay. So I want to note the following fact. So this quotient, this affine flag variety has isolated T fixed points. And these are in bijection with the extended affine Pell group. So it's this semi-direct product. And an element here just goes to, so you apply the co-character to the loop variable, and then you just permute the columns in some way. Okay. So this gives a representative of a t-fixed point in the affine flag variety. So that will come up in a moment. Okay, so here's the main theorem, which kind of answers some of the questions I posed for these Emerton Gee stacks. So the first is that, so over here I have let me call it xn red gen. So this will just be some union of irreducible components of xn red. So there's going to be some T torsor. And over here, I'll have M gen red. And again, I'll have some T torsor here. And this is an isomorphism, at least on components, on connected components. Okay. So in other words, on each connected component, this is an isomorphism, but this map collapses. So this has infinitely many connected components, and this has finitely many connected components, and it collapses some infinite set of connected components onto one, okay, in a very controlled way. So this gives a very simple presentation of the stack. So one just takes a certain T torus, and then one just takes a quotient by a different T action. So these T actions are not the same. So this map is not T equivariant, but for our purposes, it's not so important. Okay. The next fact is that if I look at the T fixed points, okay, so this is some subset of W tilde, these correspond to generic tame Galois representations. And in fact, if you remember what the T fixed points are, then this gives the inertial weights, and this gives the niveau of the Galois representation. So it's a very explicit correspondence. The next fact is that, so I'm just going to put a T to denote that this Galois representation is tame. So remember that I wanted to know, like for a given rho bar, I wanted to know what components it lies on. So it lies on the component labeled by the Serre weight sigma, if and only if sigma is in this Hertzig weight set for this rho bar. Okay. So I didn't say what the set was, but if you want, this is the definition of that set. So it gives a geometric interpretation of it. And the final fact is that if tau is tame and generic, so whenever I say generic, it just means that the inertial weights are far apart. So it's weaker than very generic. So then tau corresponds via the inertial Langlands correspondence to a Deligne-Lustig representation of GFB. Okay. And I can actually give a description of the irreducible components of this stack. So I take the reduction of this Deligne-Lustig representation, and that gives me the irreducible components. I should say that eta is just, it's the minimal regular co-character. Okay, to summarize, I answered some of the questions over here. So for one thing, this tells me something about the components that a Galois representation lies on, and this fourth part here tells me something about the components the irreducible components of one of these potentially crystalline stacks. Okay. So are there any questions? So again, this will just be a black box. And I want to use this to go back to make some deductions from the main theorem. Actually, let me bring that back up. So here's that. Here. Let me try to. I don't know if this is going to work. Okay, maybe that kind of works. Okay, so now I want to describe how to prove one implies one of the inclusions of two. Okay. And I'll just draw a picture. So, so here one has, so let me just assume that rho bar is tame, because that's what one says. Okay, so here I have the set of weights predicted by Herzig. And so yeah, maybe I should write the following down. So so if you remember from the first page, to show that a weight isn't modular, you have to, one way to show that is to show that you don't have a crystalline lift of a certain weight. Unfortunately, CR weights don't have, they don't always have lifts. So in the GL2 case, they always the CR weights always lift. So you can always lift sim A minus B to FP squared to sim A minus B ZP squared. So you always have this nice connection between the two. In this case, you don't, but you have the following. So if I have some modular CR weight, and this is a Jordan-Holder factor of a Deligne-Lustig representation, then, well, since you know cohomology with these coefficients is non-zero, necessarily cohomology with these coefficients is non-zero. And that means that rho bar has a potentially crystalline lift of type eta tau. Okay. So then the basic idea is if you have some weight sigma, which is not in this weight set, then you just find some a nice type so that it contains sigma, but it doesn't intersect with this Herzig set. And so that means that if you look over here, that means that rho bar will not lie on any of the components of x eta tau. So you're just combining these two facts here. And that means that rho bar won't have a lift of type eta tau, which means that sigma can't be in W bar bar. Okay. So I've reduced proving this to some kind of combinatorial problem of finding a good type like this. And these things have combinatorial descriptions, and so you can actually solve this. So that's this implication. Okay. The other inclusion is more difficult, and that's where you use the very generic hypothesis. But let me not say anything about that. Okay. So this argument can actually be upgraded. And this upgrade can be used to prove that 3 implies 1. So here's the upgrade. So if if I can find some tame representation, which the set of whose components contain the set of components which contain rho bar. So if I have this implication for all sigma, then I can just repeat the same argument before. So that means, so if this doesn't have a potentially crystalline lift of type eta tau, then so this one doesn't either, just by this fourth part here. So the argument from before tells me that I have this inclusion. Okay. Okay. So that gives me a strategy to prove that 3 implies 1. So if rho bar is wild, so not tame, then I'd like to do the following. I'd like to just find 2 different tame things for which this is true. And then W of rho bar has to lie in their intersection. And if these are truly different, then this will be of size smaller than either one individually. So that means that this can't be the size of this Jordan-Holder set, and it must be smaller. And this is where the geometry comes in. So the idea is to pass to the local model, because this question of lying in irreducible components can be rephrased in terms of the M red gen. So let me write this down. So here's some simple fact about the geometry of the affine flag variety. So a point here is T tilde fixed or T fixed. So T tilde fixed and T fixed are the same. If and only if I take the T tilde orbit of X, take the closure and take the T or T tilde fixed points of this set, this has size 1. Okay, so that's the proposition. So remember that T fixed points correspond to tame rho bar. So if X lies on some irreducible component, then this closure of the orbit will also lie on that, will also be contained in that component. And so this implication will be true for any T fixed point in this orbit closure. So if it's wild, that means this will imply that this has size at least 1, or strictly bigger than 1. And so I'll have multiple tame bars to which I can apply this, and I get this implication. So I think one direction is easy. So if x is T fixed, then this orbit will just be a single point. I take the closure, it's that same point. Take T fixed point, it's still a point. Okay, so it's only the backwards direction that I need to prove. Okay, so let me describe how this works. And here the point is that I'm really using the geometry of this moduli stack that Emerton Gee defined. So you wouldn't be able to see this geometry from just deformation rings. Okay, so let me define the following intergroup scheme. So we sometimes call this the negative loop group. And I want this to be upper triangular mod T inverse. Okay. So this is like the opposite Iwahori. So this is the analog of like the opposite Borel. Okay. So I wanted to define this set. Turns out to be open. Inside of this affine flag variety. Okay. And here's the crucial lemma, which isn't too difficult to prove. So these opens give a covering. Okay, so that's the first part. The second part is that if I have some variety, some finite type closed subvariety, then the intersection with U W tilde is affine. So this is pretty easy. So since this is finite type, then this will only involve some bounded denominators in T. And so it'll only involve some finite bounded amount of powers of T inverse. And that part of I minus is going to be just affine. Right? So this if I bound the powers of T inverse for this group, then it's just an affine scheme, a finite dimensional affine scheme, even affine space. And so this intersection will just be some closed subvariety in that. If, moreover, Z is T tilde stable, and this intersection is non-empty, then, in fact, W tilde lies in Z. Okay. So this actually uses something about the group actions. So recall that there's this T tilde action, and it turns out that this group I minus is T tilde stable. And so UW tilde is T tilde stable. And there's a certain GM action which contracts to the W tilde. Okay, so you can kind of see it here. So if I scale T inverse by lambda inverse and take, sorry, if I scale T by lambda, then I scale T inverse by lambda inverse. And if I take the limit as lambda goes to infinity, that gives me 0. And so that will kill the T inverse terms. And so I'm just left with a constant matrix, which is upper triangular. And then I can multiply by some dominant diagonal matrix. And the conjugation of action will kill the top part. So in this way, I can contract this group to the identity with a certain GM lying inside of T tilde. Okay, in any case, so that's how the third point is proved. So okay, so now, so these are pretty standard facts just about the affine flag variety. And let me put these together. So right, so I want to prove this proposition. Okay, so lemma gives an open affine covering of this orbit closure of size given by the number of T fixed points. Okay. So, so the second part here says that the cover by opens is actually a cover by open affines. And this last part says that to count the number of non-empty intersections, I just need to count the T fixed points. And then now it's easy to conclude. So this orbit closure is projective, just because it's closed in a projective scheme. So the affine flag variety is in projective, and it's connected, just because T tilde is. So this implies that, so I have some open affine covering of a projective thing. So yeah, so that means that it just contains a single point. So I assume that this is a size 1. And so I just get a single point here. And that tells me that X is T fixed. Okay, so I'm basically out of time. So I just, let me just put up this last sheet. So this is the second Tameness criterion. So there's this tension between the number of modular Serre weights and the number of elements in the T orbit closure. So if you had a semi-simple Galois representation, then this would only have size 1. So you wouldn't get very many T fixed points in the closure. And all this, one of the things this theorem says is that this can be made very, this could be made precise to this tension. So there's actually there's actually a numerical formula which expresses this tension. Sorry, so I didn't have time to get to that, but that's okay. So let me stop there.
Okay, so let's thank the speaker for a wonderful talk. Any questions? You may unmute your mic and ask a question.
Hi, Don. So may I ask a question about the last page? Hello?
Sure.
Yeah. So you read. So you said for the application from 3 to 1, if rho bar is wild, then you write WR bar is contained in W of rho 1 T intersect with W of rho 2 T. Maybe another page?
Yeah.
Oh, yeah, here. So what is rho 1 and rho 2?
Yeah, I should have said this. This is the strategy. So the strategy is to find these two
to find
tame representations, and the way you do that is, the way you do that is you look for T fixed points in the T tilde orbit of your representation. So you pass to the local model because all the questions are the same on the local model, and the wild thing corresponds to some X, and these will correspond to some T fixed points in the T tilde orbit closure. So all I have to show is that if this is wild, then this this set has size bigger than 1, strictly bigger than 1.
Okay.
Yeah, so that's what I show. So in fact, I show the opposite, or the contrapositive, which is that if I can only find one rho bar, then it actually has to be tame to begin with.
Thank you.
Any more questions? Okay, so we thank the speaker again.